Okay, so finally, one last item in this chapter for the entire chapter, basically, is that I'm going to try to make a connection between coupled oscillators and the wave that you have learned. Okay, so the wave, what I mean is mechanical wave. So you have a string, and then you wiggle one of the end of the string, and then you form a transverse wave. Okay, so that propagate along the string. Okay, so that kind of wave. Okay, so I believe that you have learned that. And here, I want to show you that how that kind of motion can be treated as a continuous limit for the coupled oscillator. So the system that I'm setting up here, again, is an n-particle a linear system, a linear structure, right? So, and this time, however, I'm not trying to consider the motion of the masses to be going along the line of the spring. Instead, I'm only allowing all these masses to move up and down, let's say. Okay, so just like this. And then one more thing is that at equilibrium position, let's say that all the springs are already kind of stretched out. So just like when you consider a mechanical wave in a string, right? So first of all, you have already made the string quite a bit tight. Okay, so some tension in the string. Okay, so that's why here, right? So just picture in your mind. Okay, so all these springs are already stretched. Okay, so not at their natural length anymore. So now, again, I want to set up the equations of motion for the particle. So if you look at, right, so for example, this particle over here. So what is the force? What are the forces acting on this particle? Of course, it would be due to this spring and this spring. So here, right, so you may think that, so this could be complicated, right? So because now that you have this vertical component and also horizontal component, right? However, as I said, okay, so let's say I already applied the constraint that this mass cannot move to the left or to the right, right? So I told you already, I only allow this mass to go up or down. Apply some other constraint, let's say. And so therefore, to study the motion of this mass, just need to consider the vertical component of the forces given by the two springs. Okay. So, and to do that, right, so let's look at, for example, this pair of masses. So let me draw the mass over here again. So one mass here, and then the other one here. So here I'm exaggerating the angle. Okay, I'll tell you later about the approximation that I make. But let me define the parameter first. So this is theta. Okay, so remember this distance over here is d. And let me call this length to be L. And now this vertical distance over here would be xj plus 1 minus xj. And the tension, of course, will be going along the spring like this. But as I said, I only care about the vertical component, right? So therefore, I only want to know the t sine theta. Okay, t sine theta. And that would be t times xj plus 1 minus xj divided by L. Okay. So now I we'll make approximations. Okay. So first approximation that I'm making is that this data has to be small. Okay, so that's why this picture is not a good one. So imagine that data is small. Okay. So, and in that case, right, so for small data, so let me see, right here for small data, right, sine of data is approximately equals to tangent of data. And what is tangent of data? Tangent of data is xj plus 1 minus xj divided by d. So that's approximately equals to t divided by d times the difference of the two displacements, like this. Okay, so now what about t? So this is another approximation that I'm going to make. Is that t, in principle, has to be calculated from this length, right? So because the T would be given by the restoring force of the spring, right? So the more it's stretched, in principle, you should get more restoring force, right? For example, this tension here, right, should be slightly greater than the tension here, because this spring is more stretched than this spring, right? So if you look at it. However, here is an approximation that we are making, is that we are assuming that the tension doesn't really change much, even when you go from this state to this state, right? So because you can imagine the following, right? So suppose originally the spring is already quite stretched by a lot, right? So now that you change the length a little bit further more, it's not going to change the tension by much. Okay. So therefore, I'm going to assume that this tension T does not really depend on the angle theta over here. Okay, so now if that's the case, right, so that's the force that I'm going to take. So then, of course, for each mass, you have to calculate two P, right, two forces, right? So from the two springs, so there are two tensions. So therefore, at the end, I have this equation over here, right? So due to the spring on the left and due to the spring on the right. So, but nevertheless, now if you look at the form of the equation, right? So it looks again exactly like this one, over here, right? So except that now I have this P divided by D instead of this K. And the difference between this case and the case that we are looking at now is that this is the longitudinal oscillation, right? And the one that we are looking at now is the transverse oscillation, right? So therefore, we are considering kind of a transverse wave. And similarly, in fact, you can treat this as a system that you can propagate longitudinal wave, actually. Okay, so because of the exact same mathematical formula, mathematical equations, we know that the answer for the eigenfrequency that's the same, right? So like this. So now, if I just try to show you some pictures, right? So for a simple case where n equals 3, the three normal modes will be looking like these. Okay. When R equals 1, this is the oscillation mode. So you can imagine what's going on, right? So all the three particles are oscillating in phase. So when this one go up, this one go up, this one go up. After some time, right? So you could imagine that maybe become something like this. Right? So just go up and down like this. So now what about this one? The second one is that I have one note over here. So this mass is always at rest. Okay. So after some time, right? So the mass over here will go maybe here. And at the same time, the mass over here will go up here. Right? So like this. Right, so that is this mass and this mass, they are doing out of phase oscillation, and then this one is always at rest. Okay, so similarly for this one, right? So you could imagine that after some time, right? So this mass go down, this mass go down, this one go up. Right. So that is these two masses are oscillating in phase, and this one is out of phase with respect to the other two. So just looking at these three pictures, I think it reminds you of standing waves. Right? So when you learn about standing waves, so you do have the modes, right? So the two fixed wall, one string. Right? So this is the mode with the lowest frequency. Right, so and then the next mode, this one with one note, and then the next one, right, so with two notes, and then for the continuous string, you can keep going on and on, right? So if you really have a continuous string, right, so you don't just have these three modes, you have infinitely many modes actually, right? So with more and more notes. So here we only have three because we have three particles only. And in fact, in all these three pictures, you can see that I do have the dashed lines. Okay. And these dashed lines actually represent the behavior if we actually take the continuous string as the system. So continuous string, mathematically, that means that I'm taking this capital M to infinity. Okay. So then this is how we are going to model a continuous string, okay, using n particle couple oscillator. So we are going to increase the number of particles, right? So and then basically n tends to infinity. Infinitely many particles. But at the same time, right? So because we're fitting in more and more particles, but we are not really making the system longer and longer. We are just having a fixed length of space, just fitting more and more particles. And that means the particles have to stay closer and closer together. So that is each spring has a shorter and shorter length. Therefore, n tends to infinity, and then at the same time, we require that b tends to 0. Okay. Moreover, I'm just having a system with finite masses. Okay, so I'm adding more and more particles, but at the same time, I'm keeping, let's say, the total mass of the system the same. Okay. Okay, so this is typo here. This will be m tends to 0. Okay. So the mass of each particle tends to 0. Okay. So with all these limits taken, right? So there are two quantities that are remain constant. right? The first, length, I already mentioned that, and the other, the density. So that's how I keep the total mass to remain a constant. Okay. So then now let's look at the eigenfrequency again. Right. So if we look at the same formula for the eigenfrequency, so this is what we have derived already. Right. So this is the expression. And then I just input these quantities. Okay, so to this expression here, then the omega r can be expressed as this sine function. So, however, right, so we are taking the limits, right? So if we take the limits, you'll find that this expression here will tend to this limit. So how do we actually do it? Like that, if I just write it over here, this whole thing can be written as like this. So this one is exactly equal to this one. So now we are taking the limit that d tends to 0, right? So then just recall this limit that you have learned. Sine x divided by x, as x tends to 0, the ratio tends to 1. Okay. So here, because d tends to 0, then this fraction also becomes 1. Right. So therefore, omega r will tend to this limit as we take the continuous limit. Okay. So I think this formula is something that you have seen before, right? So if you have learned that the speed of the wave propagating in a string, so you might have seen this formula, right? So the speed of wave is equal to the square root of tangent divided by mu, right? So the mu is the mass per unit length, so which is my rho over here. Right. And then furthermore, if you just also remember that omega is equal to v times k. K is the wave number, right? So you can verify that this omega, which is equal to v times k, and v is this one, you should recover this result over here. Okay. So, and okay, by the way, how do we get k? So I think you know that already because you using this picture over here. Right, so if this is the length L, so the wavelength, what is the wavelength? The wavelength, right? So the for the first fundamental mode, right? So the wavelength is 2L, right? So then the next one is L, right? And the next one 2L divided by 3, and so on, right? So, and by using this definition, k equals 2 pi divided by lambda, right? So you should be able to find the k. Right, so basically lambda is 2L divided by R, right? So R is just any integer go from 1, right? So all the way to infinity, right? So that's why this K is 2 pi divided by 2L times R, right? Just R pi divided by L, right? So, and I'm not sure if you have learned that before, but this result, V equals square root T divided by mu, can also be directly derived, okay, so from considering the wave equation. Okay. So, or I should say, not considering the wave equation, I should actually put it this way. The wave equation itself can be derived from starting by considering a continuous string. Okay, not sure if you have learned that before, but you will, I think. Okay, and this V square, when you derive the wave equation, this V square, okay, will be given by this. Okay. So in fact, if you want to see how this wave equation is derived, okay, so which is not included in this course, so you can go to the textbook, not the chapter on coupled oscillator, but the chapter on the continuous wave system. Okay. Okay, so so this is the end of chapter 4. So for the midterm test will include the content. Okay, so up to this point. Okay, chapter 1 to chapter 4. Okay. So some of the optional contents won't be included in the midterm. I will make a list. Okay, so and upload it to Blackboard. But roughly speaking, okay, so the first 4 chapters for the midterm. And now, okay, so let's take a break, 15 minutes break, and then we'll start a new chapter on Hamiltonian mechanics. Okay, so I want to remind you that the homework 4 is posted. So it's still next Saturday. Date was wrong. Okay. Okay, so let's move on to the next chapter. So next chapter is about Hamiltonian mechanics. Okay, so this is closely related to chapter 2 on the Lagrangian mechanics. Okay, so before I actually get into the lecture notes of the chapter itself, so I want to first use an example here to introduce the concept of the so-called Legendre transform. Okay, so I want you to look at this picture over here. Okay, so what we have is just a very simple function, which is the x squared. Okay, so fx equals x squared. This is a function. So now look at the red line. The red line is just the tangent of this function at this value x0. Okay. So the equation of the tangent of that straight line, right? So it's simply given by y equals f prime x0 x plus c. Right, so because we call that the equation of straight line is y equals mx plus c, right? So m is the slope, right? The slope is f prime x0 in this case, and c is the y-intercept. So it's located over here, c. Okay, so what you could imagine is that if you are taking another value of x naught, right? So you will be having another tangent line, right? So for example, this point, if you draw a tangent line, then that would be something like this, right? And that means the y-intercept will move from this point to this point, right? So that's the straightforward, right? So nothing is new here. You have learned all this. So now let me express C as the following. So C is equals to y minus f prime x naught times x, right? Just rearranging the terms. So I actually want to find out the value of C. I pick an x naught for you. I actually want to find out C. Then what do you do? Okay, so then you can go back to this equation, right? Substitute a pair of value for x and y that we know, right? So we know that at this point, the coordinate xy is equals to x naught and f x naught. Okay. So therefore, I'm going to just put y as f x naught and then x as x naught. Right. So this is a formula that you would use. Whatever x naught I give you, you use this formula, you give me the value of C. So then now you can see that C is a function of x naught, right? So this x naught that you pick, okay. And I'll just simply say that C is a function of x, right? So you just call this x, okay. So this is a kind of a new function, right? So but this new function is closely related to the original function that we were talking about, the x squared. Okay. So now I'm going to define a function. So define g as f minus x times f prime. Okay, so essentially, so the g function is the c function. Okay, so but I'm just going to call this g, okay, in the discussions following. Okay. So now, so this is a function, as I said, is closely related to the x squared function. Okay, so I want to actually work out the expression for g in this case, right? So this g in this case would be equal to, what is f? F is x squared, right? So x squared minus x times, and what is f prime? F prime is this, right? So then it would be 2x, and that would be minus x squared. Okay. So then if you want to plot the curve for the g, and this will just be an inverted parabola like this. So now I want to express g, okay, so not as a function of x, but as a function of f prime. Okay. So right now, this expression over here, I can say that g as a function of x is minus x squared. But what I am asking is the expression of g, I want to express it as a function of f prime. And let me let me call let me give a new name to the f prime. So let u equals f prime. So that is to say, I want to find g as a function of u. Okay, what is the expression for that? So, well, you know that this f prime is equals to ddx x squared, right? So this is just 2x, right? So that is, okay, so let me write them out separately. So therefore, x is just u divided by 2. Right, so therefore, right, so g is minus x squared, which is minus u divided by 2 squared. So that is just minus u squared divided by 4. Right, so g of u is minus u squared divided by 4. I don't want this anymore. So this is the Legendre transform. Okay, so what have we just done? Right, so we go from f of x, and then by using this definition, we get another function g of u. So this process is called the Legendre transform. Okay. So, but what is the geometric meaning here? Right. So as I mentioned at the beginning, right. So g is a function that tells me the value of the y-intercept of the original function that we are considering. Right. So g, now I want to call it as a function of u. So what does that mean? So that means that suppose I tell you the slope of the tangent, right? So for the original function, right? So that would be u, right? So that because u is the f prime, right? So I tell you that slope, and then the g function will tell me the y-intercept, right? So of that tangent. So that's what g is giving me. So that is g. You can treat g as an alternative representation of f itself. So if I tell you the function, the most direct way is that I give you the expression of f of x, right? So that is for a particular for any value of x, I give you the value of f of x. Then you can directly draw the function out, right? However, this time I don't tell you the form of the original function. So that is just pretend that you don't know x squared, f of x equals x squared. But what I'm telling you this time is that for any slope of the tangent, okay, so I tell you the value of the y-intercept c. So you could imagine that using this function, okay, you can actually get back to the original function, right? So because if you use this function function g, what you'll be getting would be a bunch of many tangent lines, and each tangent line you know the y-intercept, right? So with this whole bunch of tangent lines, right? So if you draw a curve that is touching all these tangent lines, then that must be the original functions that we are talking about, right? So that is, right? So G, again, is an alternative representation of the same function f. Okay. We don't lose any information. Okay, so from going from f to g. Okay, so now let me rewrite what we have just did here. And then there's some small details over here. You need to be more careful. Okay, so f of x, right? So the Legendre transform. So now imagine that if I give you g of u, so this time if I just give you g of u without giving you f of x, so then what you need to do to get back to f of x, what you need to do is the following. Okay, so f of x. So from this definition here, you can see that f has to be equal to c plus x times u. Okay, so there's one change I would like to make here. Okay, so it is just a convention. So instead of calling g to be f minus x times u, we will be adding a minus sign in front. So x times u minus f. Okay. So if that's the case, then f is no longer g plus xu, right? So f has to be xu minus g. Okay, so this step is nothing but a convention. Okay, so we are not changing the whole idea. Okay, so we are still following the whole idea, just giving a minus sign in the process. Okay. So e is a function of u. So that means by definition, I can say that, right? So dg is equal to dg du du. Right. So because for any function, right? So as long as it is differentiable, I can write it this way. But the total differential equals to this derivative times du. Okay. So on the other hand, right, the form of the g is this one, right? So if I just take the total differential directly, so then dg would be d xu minus df, and that would be x du plus u dx minus df. But again, what is df? Right, so by definition, right, so df can be written as df dx dx, right? And remember, we call df dx as u. So therefore, df is also u dx. So then dg would be just x du. So now compare what we have here and here. So that is to say, when you do this kind of, right, so Legendre transform, right, so x du dx dg du has to be equal to x. Okay. And then in the previous slide, I said that u has to be equal to dg du. No, u has to be, sorry, u has to be equal to df dx. Okay. Right, so that is when you do this kind of transform, okay, these two relations are automatically has to be satisfied. Okay, so now let's go back to the previous example. Right, so I'm doing things the other way around. Right, is that I'm going to tell you g of u is equals to u squared divided by 4. Right, so here. So I don't have the minus sign anymore because, as I said, here I changed the convention. Right, so if you use this convention instead of this convention, you will tell me that g of u is u squared divided by 4, not minus u squared divided by 4. Okay, so what I'm trying to do is that I give you this g of u. Pretend that you don't know f of x. I want you to find out the form of f of x by just using the Legendre transform one more time. Okay. So that is to say, I'm going to use this formula. And at the end, I want f to be expressed as a function of x, not a function of u. Okay. So here, using this relation, know that x has to be equal to dg du, and dg du is just u divided by 2. Right. So therefore, u is 2x. Okay. And f now can be written as x times u, which is x times 2x minus g. G is u squared divided by 4, which is 2x squared divided by 4. So, and then at the end, what do you have? What do we have here? So x times 2x, which is 2x squared. So minus the second term, which is just x squared. And that would be x squared. So we exactly get back to the original function, f of x. Right. So notice that, right? So in the whole process, right? So we pretend that we don't know f of x. Right. So all I'm doing is to use this definition of the Legendre transform with these two with this relation. Okay. Get back to the function x. Okay. So from this simple example, right? So I show you that how the f and g are just kind of the two different representations of the same function. Okay. So one small remark over here is that Legendre transform cannot be just applied to any function. Okay. Sometimes it doesn't work, but we will be just focusing on the case where Legendre transform can be applied anyway. But I just want to mention that when it won't work. So here you can just try to look at this function. Okay, so this time the function I'm referring to, let's say, is f of x equals minus cosine x. Okay. So now you can see that this tangent and this tangent have the same slope, right? But clearly, the two tangent lines have different y-intercept, right? So this is, let me call this C1 and this is C2, right? So then this is the case when Legendre transform won't work, okay? Because to construct a function of u, right? So that means that I give you one value of slope, it just gives me one unique number. But here it won't work because I give you one number of u, which is one slope. It can be either giving me this C1 or this C2. So then you cannot construct a function that way. So that is to say, to require the whole thing to work, okay, so the f of x has to be always having the same sign. Okay. So has to be, I'm sorry, that's not what I want to say. This f prime of x has to be a monotonic function. Okay, has to be a monotonic function. Okay. So because in this case, right, so f prime of x would be sine of x, right? So the sine of x, I draw the same picture, right? So it would be like this. So this is not a f prime of x is not a monotonic function. It's sometimes increasing and then decreasing back again. For the x squared, I don't have the problem, right? F prime is also always increasing. It's a monotonic function. Okay, so then this is the mathematical preliminary that we need for the coming part. Okay, Hamiltonian mechanics. Okay, so what we are trying to do in the first part is that we have a function that we learned in chapter 2, which is known as the Lagrangian. Okay, so we want to use an alternative representation. Okay, so for this Lagrangian, so that is we want to apply Legendre transform. Okay, so to this Lagrangian function. Okay, after the Legendre transform, the function we get is called the Hamiltonian. Okay. So, but you could imagine that we are describing the whole the same physical system. Okay, just like the example I show you, right? So from the f of x to the g of u, we are really describing the same thing, but with different representation. So therefore, here we are going from Lagrangian to Hamiltonian, but we are describing still the same physical system. Okay, so then let's. Okay, I still have 5 minutes. I can maybe get to a couple more slides. So Legendre transform. So the example I just gave you is a function of one variable. Okay. So now let's go to function of multiple variables. So this time I have a function of two variables, f, x, and y. So let me just briefly write down what we have just done. So before, what we did, f of x, do the transform, get to the g of u. So this time, what we are trying to do is f of xy, and then go to g of uy. This is what we are trying to do now. Okay. So, but we are not. We are keeping the y variable. Okay. So we are just changing the x variable to the u variable. Okay. So okay. So this is the function that we are considering, f of xy. So for the two variable function, the total differential is written like that. Right, so u is partial f partial x, v is partial f partial y. So now we generate this new function, right? So you've seen this already, u of x minus f. Then again, consider the total differential of this g function. Then this d of g would be equals to this dux minus df. Okay. And last time for df, we only have one term. But now, because because f is the two variable function, that's why df has two terms now listed here. But the idea is really the same. Right, so now I have these two terms, and then subtract by these two terms. Then you see that this dg is equals to this xdu minus v dy. So then you can see that g is a function of u and y. Okay. So then we have accomplished the goal, right? So it's the same thing as we have just did. Okay. So now again, if I look at the dg itself, right? So if I just tell you that g is a function of u and y, and I don't tell you anything else, then still you can tell me that dg must take this form. Right. So now compare this equation with this equation over here. Okay, so x is equals to partial g partial u. So before what we had, we had x equals dg du in the previous example. So now x is partial g partial u. Right. Similarly, before u was defined as df dx. So now u is partial f partial x. Right. So because two variable functions. All right. So again, similar diagram here. Okay. So f of x, using this definition to get to g of u. Okay. So the u, right? So it looks like a new variable, but as you have seen already in the previous example, u is actually representing, right? So the slope of the tangent of the original function. Okay, so u is this. And then these two relations are always implied whenever you apply the Legendre transformation. Okay. So let's look at one more example over here. Okay. So f of x, I give you a function of two variables, right? So it's equals to this 1 plus x squared times y squared. Okay. And now I want it to become this new function. Okay, g of x and p. So I replace y by p. Okay. So and then following the same recipe, right? So this p has to be equals to this partial f partial y. Right? So you actually do the derivatives, then this is what you have. So now that means y is equals to p divided by this thing, right? So and then g, again by definition, given by py minus f. So and at the end, I just express everything in terms of x or p, right? So eliminate y. So then this is what we have. Okay, so one good exercise. Okay, so let me just the last exercise here is that now you pretend that you don't know fxy. Okay. Just take this gxp. Try to do the Legendre transform one more time, and then to verify that you can get back to fxy. Okay. Let's take maybe 2 more minutes to finish this. Right, so again, just following the same definition, right? So gxp, we apply this transform. Right, so now I want to get back for, to fxy from gxp, right? Replace p by y. And also, right, so y has to be equals to this partial g partial p. So that is partial p squared divided by 4 1 plus x squared. And that would be just p divided by 2 1 plus x squared. Right, so that is p is 2y 1 plus x squared. Right, so finally, right, so f is y times p. P is this whole thing, 2y 1 plus x squared minus g. G would be p squared, and p squared is this whole thing squared. So 2y squared 1 plus x squared all squared. And then after simplification, let's skip that. You should get back to this. Right. Yeah, try to make sure that you know the procedures. Okay, so that should be straightforward. Okay, so just basically follow this line. Okay. Okay, I think okay, I have to stop here for today. So next time, okay, so we will actually show you how to use Legendre transform. Okay, so to convert the Lagrangian to Hamiltonian.